Today, let us discuss on Stokes' theorem. What is Stokes' theorem? It is actually the first generalization of Green's theorem. It is just another version of Green's theorem in higher dimension. Let us read out the definition of Stokes' theorem. If S denotes an original surface relative to the sense of description of its boundary curve C, and f, g, h are three functions of x, y, and z which are continuous and which possess continuous first order partial derivatives at each point of a domain containing S, then we have the curve integral over C f dx plus g dy plus h dz is equal to the surface integral over the surface S, then del h del chi del z dy dz plus del f del z minus del h del x dz dx plus del chi del x minus del f del y dx dy. In Stokes' theorem, we are going to relate the curve integral with the surface integral. If S is a surface, then the curve which we are going to integrate over will be the boundary curve of the surface S itself. Now, these three functions f, g, and h are the functions in three variables, or they have a domain in R3. Now, let us discuss one problem on Stokes' theorem. In this problem, we are going to verify Stokes' theorem in computing the line integral or curve integral, the curve integral over rho x square y square dx plus dy plus z dz, where rho is the circle x square plus y square equal to a square and z equal to 0. Actually, this x square plus y square equal to a square in R3 is an equation of a cylinder. But since we're having z equal to 0, so this rho is going to be a circle in the xy plane. Our z is equal to 0. Let us write a solution. The boundary rho is a circle with equation x square plus y square equal to a square, and it will be on the xy plane, so our z is equal to 0. Since this equation represents a circle, so if we write the parametric equation of a circle in xy plane, what we have? Whose parametric equations are x equal to a cos t and y equal to a sine t and our z equal to 0. T will vary from 0 to 2 pi. If we draw the xy plane, And if we draw a circle on the xy plane whose center is at origin O and whose radius is equal to A, then this is our rho. Now what do we get from here? We have dx equal to minus A sine t dt. From here we have dy equal to A cos t dt. And from here z equal to 0, we're going to get dz equal to 0. Let us find the Girth integral first. Therefore, the Girth integral will be x square y cube dx plus dy plus z dz. We have parameterized the variables x, y, and z, so we're going to get substitute the value of x, it will be a cos t whole thing square. The value of y, which is a sine t, we're going to have a sine t cube. Then dx, we're going to get minus a sine t dt. Plus this term here, dy will be a cos t dt plus z is equal to 0 and rdz is also 0. Here only the variable t will vary from 0 to 2 pi. Then you're going to have 0 to 2 pi. If you complete the calculation, you'll get a 6 cos square t sine to the power 4t plus a cos t dt. I will leave the calculation steps here. You calculate using the reduction formula. Then you will get minus pi a to the power 6 by 8. So we have got the Girth integral, which is minus pi a to the power 6 by 8. Since we have to verify Stokes' theorem, then we also have to find out, this is Stokes' theorem. We already found this Girth integral. Now we're going to find out this surface integral. Now comparing with this Girth integral, This is x, sorry, this is f, or g will be equal to 1, and our set here, which is h. These are the value of f, g, and h. What do we need in order to find out the surface integral? We need to differentiate h with respect to y, g with respect to z, then del f del z, del h del x, del g del x, and del f del y. So we're going to get by differentiating f, g, and h. Therefore, del f del y is equal to 3x square y square. Del f del z, we have no z, so it will be equal to 0. Del g del z, we have no g, so we have no z, then it will be equal to 0. Del g del x is also equal to 0. Next, del h del x equal to 0. Del h del y is also equal to 0. Now our integral I, which is the surface integral over S, del h del y minus del g del z dy dz plus del f del z minus del h del x dz dx. Let me continue here. Plus del g del x minus del f del y dx dy. Substitute all the values, integrate over s, or del h del y is 0 minus del g del z, which is equal to 0 with respect to dy dz, plus del f del z, which is 0 minus del h del x, which is 0 dz dx, plus del g del x, which is 0 minus del f del y, which is 3x square y square dx dy. From here we are going to get 0, so we are going to get only from this term here, which is minus 3x square y square dx dy. Now what is S? If we draw a row, which is the boundary curve for S, row in the xy plane, it is a circle with center at the origin and having radius a. Since this is the boundary curve, of S, so S is going to be this surface. It is a surface inside this circle of radius a. So our S in xy plane. Now let us try solving out this surface integral. If we change the variables, if we change it, the variables to polar coordinates, change this to polar coordinates, we have x equal to r cos theta, y equal to r sin theta. Here both r and theta will vary. Theta is the angle, so it will vary from 0 to 2 pi. Theta will vary from 0 to 2 pi. Since we have all the points inside this circle, even the radius, this r is going to vary from 0 to a. R will vary from 0 to a. Since we're changing the variables, so we need to find out the Jacobian. J del x del r del x del theta del y del r del y del theta. If we calculate for this Jacobian, then we'll get the Jacobian equal to r. Then this integral will change to, therefore I, which is this surface integral, will change to the integral that's put for r which is from 0 to a, and theta which is from 0 to 2 pi. Then we have minus 3. Let's take minus 3 outside. Then x square, or x is r cos theta, so r cos theta whole thing square, or y square, so it will be, or y is r sin theta whole thing square. Then the Jacobian, or Jacobian is r. Since r is positive, so modulus of this Jacobian will be r. Then we are changing it to the variable dr d theta. If we try to calculate this, then we are going to get the answer equal to minus a to the power 6 pi by 8. Or if we rearrange, we get equal to minus pi a to the power 6 by 8. Hence we get the same answer as the Girth integral. From the Girth integral we get minus pi a to the power 6 by 8. Therefore we have verified Stokes' theorem. Since This curve integral is equal to the surface integral.